right, you guys, so now that we know what non-uniform motion is, we have to learn how to graph it. But before we do that, I do just want to do a little bit of review of graphing uniform motion, which remember is when it's covering the exact same distance in the exact same time intervals. So here I have a table that tells me the time and the distance from the start point. Okay, so of course time needs to be always on the x-axis and distance on the y-axis. And furthermore, on this guy, it doesn't have units, so I better put that there. So time is in seconds and distance is in meters. Okay, and so I want to graph this. So my time goes from 0 to 10. So the scale on the x-axis needs to go from 0 to 10. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, look at that, 10. Thing. So I'm just going to mark every 2. How about that? So that'll be 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds. Okay, and then my distance needs to go from 0 to 50. So I'm pretty sure if I do every line being 5, I should be able to get there. So the first one will be 5, but I'll only mark every other one. So then that guy will be 10. 15, then this guy will be 20, 25, this guy will be 30, 35, 40. Looks like I'm running out of room. So, but this pretty much looks like it's at 50. So I'm just kind of gonna extend my graph a little bit. Okay, so we're just gonna extend that a little bit there. I think that's going to be the new intersection. Okay, so now I'm going to plot all these points. Okay, my first point is 0, 0, so that guy's right there, okay? And then I have 2, 10, so that guy's right there. We got 4, 20, right there. We got 6 and 30. There we go. We have 8 and 40. And we have 10 and 50. So that guy will be right there. Okay, so this is our uniform motion. This is clearly uniform motion. Sorry guys, I can't use a ruler with this, so it's not going to be a perfectly straight line. Okay, so that's as straight as the line as I'm going to get. But please, please, please do use a ruler when you're doing this. I always do when I'm using paper and pencil, but it's a little bit different here. Okay, so this is clearly uniform motion because the distance time graph shows us a nice straight line, meaning we are covering the exact same distance over time. Here's a question. Do you guys remember with a graph like this, that's uniform motion, how do we find the speed that this thing is going? What's the speed of the object? What do we have to do? We have to find the slope. Okay, so we need 2 points on the graph. Again, I like to use 2 points that aren't already there. So I'm going to use this point. What's that point right there? That is 1 and 5. Okay. And then let's go for this guy right here. That point is 7 and 35. Okay, so I'm going to rewrite those 2 points here. So we had 1 and 5, and then we had 7 and 35. Okay, so remember, our slope is y2 minus y1 over x2 minus x1. So I'm going to call this x1 and y1, and I'm going to call this x2 and y2. Okay? So when I go to find my slope, I know exactly what to plug in where. Okay, so again, just change in y divided by the change in x. That's all you got to do. So the change in y would be 35 minus 5 here. And then my change in x would be 7 minus 1. Okay, so 35 minus 5 is 30. 7 minus 1 is 6. And what's 30 divided by 6? That is 5, okay? And then, of course, our units are meters per second because these guys were meters. These guys were seconds, right? And we got 5 meters per second. So I should probably put a 0.0 on there because it looks like it should actually have 2 significant digits. There we go. So that is how you find speed from a distance time graph. So just a little refresher for you there. I know we've done it before, but it's nice to have those reminders. Okay, so let's get on to non-uniform motion. What might it look when we have non-uniform motion? So instead of distance, you see in this case it says position instead of distance. That's, well, your first tip that, oh, this might not be distance. It looks like it's position, which is kind of the same as displacement. Okay, but this table, this is a yucky table. This is not good. Time should actually be on the left and position should be on the right because we know what always goes on the x-axis? Time. Okay, so don't let that mess you up. And then on the y-axis, we have position. And we are going east. And then we need to figure out the scale. So time goes from 0 to 10. So it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like just every one has to be 1 second. Okay, so I'm just gonna, again, only label every other one just to make my life a little bit easier. Okay, and position needs to go from 0 to 25. So I'm guessing we might be able to go up by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Yes, okay, we're gonna go up by 2s. Never go up by 3s, by the way. 3s are the worst, okay? I've seen it so many times because people are like, well, I can reach more. No, just don't do it. Okay, and now we are going to plot the points on this graph. So we first have a point at 0, 0. Oh, that's nice. And again, we're reading these the other way, okay? These are our x coordinates. These are our y coordinates. So it is backwards, so be careful. So the next one is 2, 1. So when x is 2, or the time is 2, then this guy's at 1. Okay, so that didn't go up very much, did it? Okay, and then the next one we have is 4, 4. Well, that one's nice and easy to not mess up. Okay, what do we have next? Next we have 6 and then 9. So at 6 we have 9. So that's halfway in between 8 and 10. That's about right there. Then we have 8, 16. And that guy was right there. And then we have 10 and 25. 25 is all the way up here. Does that look like a straight line to you? It definitely does not look like a straight line to me. Oh my goodness, maybe it's because it's not uniform motion, right? Because with uniform motion, we know what's happening. It's the same distance over the same time. So all this is telling us is it's not the same distance over the same amount of time, right? The same interval. So the graph, in this case, I'm not going to draw a line of best fit. I'm going to draw a curve of best fit, and it's going to look a little something like this. Okay? And so that is what a position time graph looks like if we have non-uniform motion, if something is accelerating. So here we go. This is something that's accelerating. This is something that's speeding up. The question is, how do I know it's speeding up? Well, if the slope of the line is gradually increasing, then the velocity or acceleration is increasing. So what do I mean by that? I mean, take a point right here. Say, what if I just drew a line just at that goes through that point but doesn't like go through any of the other points? What would the slope of that line look like? It would look like something like that, right? Okay, do that with like the highest point you have. If I have a line that just touched that point and none of the other ones on the graph, it would look something like that. Oh, that's a lot steeper than the one before, isn't it? Okay, so that means it's going faster here than it is here. This is a slower bit. So it's just saying, oh, well, look, the line is getting steeper and steeper as we go along. So this guy is speeding up. Okay? So if the opposite happens, if it starts like really steep and then gets shallower and shallower, then that is something that where the acceleration of the object is decreasing, okay? Or the velocity is decreasing. And we'll look at something like that very soon, okay? Just a note, position time graphs can also be called displacement time graphs. It could be either, so don't get confused if sometimes I call it a displacement time graph and sometimes I call it a position time graph. We know both position and displacement mean that we care about direction. So therefore, we know that those are the ones that will give us velocity and acceleration. Okay, so just a little note there. So here's what our position time graphs can look like. So of course, we already looked at one like this first one. So this is of course increasing. So this is speeding up. Again, if I take a point down here and draw a line that only touches it right there, and then if I do one here, it's like, oh, whoa, the line has gotten way steeper. But this one, again, if I take a point there and draw a line that kind of just goes along, it's a nice steep line. And then one at the end, and just draw a line there. Oh, it's gotten shallower. So therefore, this one is slowing down. Okay, so again, is the curve getting steeper or is it getting shallower? And that's going to tell you if something is speeding up or slowing down. Okay, so if we take these displacement time graphs, they always correspond to certain velocity time graphs. Okay, so this is one where we know is uniform motion. Anytime you see a straight line on a displacement time graph, it's uniform motion. So what does that mean? It means velocity is not changing, so it corresponds to a graph like that, where velocity is constant. Velocity is not changing. And if velocity is not changing, that means there's no acceleration. Okay? But of course, something like this, we know, and the second one, we know it's speeding up, right? So what would our velocity time graph look like? It looked like something like this, where we start with a smaller velocity and end at a higher velocity, right? So it looks like a positive slope of a graph. So that is something that's speeding up, okay? And then, of course, this one we know is slowing down. So if we want to say, well, what would a corresponding velocity time graph look like for that? It would look something like that, where we're starting with a bigger velocity and it's getting smaller, right? The velocity is going down. Here the velocity was going up. Now the velocity is going down, which means, of course, it is slowing down. Okay, so there we go. That is graphing non-uniform motion. However, with graphing non-uniform motion, we can find out a bunch of new things from these graphs, okay? Specifically velocity time graphs. When it's not just a straight horizontal line anymore, we can use this velocity time graph to find two different things. So there is actually so much information to be gleaned from a velocity time graph like this. So say I have a velocity time graph and I want to find the acceleration. Okay, well, first of all, look at this velocity time graph. There's actually three sections, so I'm going to kind of put it into its three sections here, right? A, B, and C. What do you notice about A and C? There's no acceleration, right? So no acceleration here. At C or at A. Okay, so I'm not gonna actually worry about either of those. So just for section B, I'm gonna find the slope, and that slope will find me the acceleration for section B. Okay, so that's all I really care about right now. acceleration for section B. Okay, and then again, that's just finding slope. So let's find 2 points on this graph. It's not as easy to read, but I'm sure we can do it. Just to note, it looks like every one of these little guys is 1. So there's 1, 2, 3, 4, and then we have 5. So that's going to help me in figuring out. So then that'll be 6, 7, 8, 9, 10. Okay. And then, oops, 11, 12, 13, 14. Okay, now I'm going to find 2 points. It's just so difficult to read it before, hey? Okay, so let's try to figure out what we got here. I'm going to zoom in a little bit just to make my life a little bit easier. Look at this one right here. That looks like something that we could work with. Kind of looks like it's going through 2, 3, doesn't it? So let's start with that one. And I'm going to go to the other side and look for something else that's kind of helpful here. I'm going to go for that one there. That looks like it's 4, and then looks like we have lines up there. So that's 6, 7, 8. Okay, so 2, 3, and 4, 8, and that's going to help us find our slope. Okay, let's do it. So again, here I'm going to do x1, y1, x2, y2. And I'm not even going to write it out now. So we can do 8, and that would be meters per second minus 3 meters per second divided by 4 seconds minus 2 seconds. Okay, what do we got? We got 5 meters per second divided by 2 seconds. What's 5 divided by 2? It is 2.5. And then, of course, that is acceleration. You see how it's like you have 2 seconds on the bottom of the fraction? That's where the seconds squared comes from. And there we go. There's our acceleration of that graph. Okay, so if I want to find the acceleration of velocity time graph, then you find the slope. So just remember, there's 2 different situations where we find the slope. That's going to be the most challenging thing. Just making sure that if you have uniform motion, distance time graph, the slope tells you the speed. And then if you have non-uniform motion and a velocity time graph, the slope tells you the acceleration. Okay? And if you put in your units here, it really does help, okay? So that's why I always write the units there, because I was like meters per second. Oh, that sounds like meters per second squared, doesn't it? One more thing a velocity time graph can tell you is the displacement. How the heck are we going to do that? Well, here it says that the area between the graph and the x-axis is the displacement. Okay, what? The area between the graph is the line, right? And the x-axis, that's this guy right here, is the displacement. So what the heck does that mean? Well, the graph ends there, so all this area, find the area of that. That actually tells me displacement. However, how the heck do I find area of that? Well, right now it looks like a shape that we can't find area of, but say I draw a line right there. Now that looks like 2 different things that we can find the area of, right? Here we have a triangle. Here we have a rectangle. So I just need to find the area of the 2 different things, and then I need to add them together. Okay? The only thing that sucks is this is kind of a weird point right here. Okay. Maybe I shouldn't have chose this graph. Okay, so I just want to find the base of this triangle, and then I need the height of it, okay? So the base looks like it goes from 0.8 to 5.8. By the way, we will make it much easier on you guys. I had to choose this graph, and I didn't even realize just how tricky this was, so I apologize. And then I need to figure out what point this is on the y-axis to get my height. Okay, so it looks like 11, 12, 12 and a half. Oh yeah, it will be so much easier to you guys. 12, so that's 12.5. Ick, I'm sorry, I apologize. Okay, we'll give you much nicer areas. So that means the base of my triangle, so if this is triangle 1, it looks like it has a height of 12.5 meters per second. I know I'm still putting the units on there. Looks like it has base length of 5 because we have to subtract this little bit from there because it doesn't go all the way there. So then it has a base length of 5 seconds. Okay, how do I find the area of this? It's base times height divided by 2. That's how you find the area of a triangle if you forgot. Okay, so again, that's just 5 seconds times 12.5 meters per second. And then divide that by 2. So the area there is equal to 31.25. And the units you do get are meters. All right, and then we are going to find the area of section 2 here. So I got to find what are the base and height. It has the same height as before, so that also has 12.5 meters per second as its height. But let's find the base. So it goes from 5.8 to what looks like, oh, right at 8. Okay, so what's that distance from 5.8 to 0.8? Well, you can just subtract 5.8 from 8 to get that distance, and that is 2.2. Okay, so here the distance is 2.2 meters. Nope, never mind, seconds. Okay, so let's find the area of this, and this is just a rectangle, so it's base times height. Okay, so the base here is 2.2 seconds, and the height is 12.5 meters per second. Okay, and what we get is 27.5 meters, and then to find the full displacement, we just add those together. Okay, so that gets us that the total displacement is 58.75. Now, when we're just doing graphs, we can't really trust the significant digits, right? So here, just the full 4 significant digits is fine. Okay? There we go. So there's 2 things a velocity time graph can tell you. It can tell you acceleration using slope, or it can tell you displacement using area, okay? So that makes it a little bit more difficult than the distance time graph that can just tell you one thing, and that is velocity. Well, it can tell you acceleration because the acceleration is 0. So isn't that nice? Okay, so it's definitely a little bit more complicated for sure. So just make sure you do a few practice questions where you have to find acceleration and displacement from a velocity time graph. Okay, so now I'm just going to quiz you a little bit, make sure we know how to read graphs and we can tell what's going on in the following graphs. So here's a velocity time graph or a speed time graph, but since the speed is changing, it looks like this should actually say velocity, so just so you know. Okay, so I want to know what's happening in each section. Okay, well, let's talk about section A first. What's happening to the velocity there? It's getting bigger. So the velocity is increasing. All right, so that means that this is speeding up. And we're assuming that this is speeding up in a positive direction, so acceleration is positive. Okay, what's happening at B? It's a straight line on a speed time graph. What does that mean? It means it's constant velocity. So this is uniform motion. So we can have both happening on the same graph. So that means that there is no acceleration. Okay, what's happening at C? Again, it's going from 15 to 25, so we're speeding up again. Okay, and so therefore, if I'm assuming we're speeding up in a positive direction, so our acceleration is positive. Okay, and then of course at D, what's happening? The velocity is going from 25 down to 0. So what's happening there? We are slowing down. Now, the thing is still going forward, right? So therefore, our acceleration must be working against it. So in this case, my acceleration must be negative. Okay, because it is slowing down, but it's still going forward.